OS Deadlocks Part 4. So before continuing this video, I recommend you to watch the 3 parts of the deadlocks for better understanding. We are going to see the deadlock avoidance mechanism in this video. So the algorithm used for deadlock avoidance is Banker's algorithm. Let's see what the algorithm says. First, we need to decide the state of the system. We are going to decide the system is in safe state or unsafe state based on the Banker's algorithm. So the parameters we are going to use is maximum is an two-dimensional array, allocation is also a two-dimensional array, need is one more two-dimensional array, and then available is a single dimensional array. So we will see what maximum is, what allocation is, what need is, and what available is in a while of time. So let us assume there are n processes and there are m resources available. Max of nm actually says what are all the maximum resources needed for each of the n processes for the m resources, right? The allocation is, so the resources allocated for those n processes having these m types of resources. So need is in future how many resources for each of the processes will be needed to complete its task. Available is the resources available, each of these resource types, m resource types, right, available. So these are the terms used in Banker's algorithm. Let us assume at an instance ij, process pi request resource rj. So we can identify that based on the max of ij tells, so what is the maximum resources j required by process pi. Similarly, allocation of ij tells, so how many resources of resource j type is allocated to process I. Need of ij tells us that how many resources in future that resource j is needed by process pi. Available of j will tell us that how many resources of type rj is available to us. For better understanding of the Banker's algorithm, let's see an example now. So here in this example, they have given there are n processes p1, p2, p3, p4, p5, right? So the n is equal to 5 represents there are 5 processes. M is equal to 1 represents there is a resource type R. Here, let's say P1 totally needs 10 resources of type R to complete its task. So at time t, it is allocated 5 resources of type R. So how many resources will it need in future? See, maximum is 10, allocated is 5. So the remaining need will be 5 more resources, right, to complete its task in future. Similarly, we'll see for process 2. For process 2, maximum resources to complete its task is 5. At time t, the allocated resource is 2. So what will be the need? Need will be maximum minus allocation, which is 3. Similarly, you can carry on for all the remaining processes P3, P4 and P5. Now, the available remaining resource of R is 2. So 2 instances of resources R is available now. Now we have to check whether the system is in safe state or not. If the system is not in safe state, there is a chance of deadlock. You have to keep in mind that deadlock always implies unsafe state. But unsafe state doesn't always imply deadlock, right? So you have to keep this note in mind. Fine. So always deadlock will lead to an unsafe state, but not all unsafe states can lead to deadlock. So now what is a safe state and what is an unsafe state? So what is an safe state now? So if all the processes can complete its task with the available resources, right? So all the needs can be completed by the available resources, then the system will be in safe state. If the available resource can't give its resources to all the needed processes, then all the processes will be blocked, right? Then the system will be in unsafe state. Fine. So now let's check whether the system is in safe state or not. Here the available resource is 2, right? At time t, let's say P1 requires 5 resources. At time t, P2 requires 3 resources, P3 requires 6 resources, P4 requires 10 resources, and P5 requires 4 resources. See here, all the process requests, right, all the process needs are greater than the available resources. Even if I give 2 here, right, so the remaining need will be 3 to complete its task. Then the available will become 0, right? I cannot give to any other process since my available becomes 0. So this example will lead to an unsafe state. So this is an example of a deadlock. The Banker's algorithm says how to avoid a deadlock. So let's see another example. At time t, there are 5 processes and 3 resources named A, B, C. So A is one resource type, B is another resource type, C is another resource type. Okay. Similarly, all the attributes will be there, like maximum, allocation, need, and available will be there. So process P0 at maximum will request resource type A, B, C 753. Similarly, for process P1 322, process P2 902, process P3 222, process P4 433. So the allocated resources at time t for process P0 is, so only B of resource type 1 is allocated, others are 0. What will be by need? As we have seen in the previous example, need is maximum minus allocation, right? There's 7. So same instance resource type, you have to subtract it. 7 minus 0 is 7. 5 minus 1 is 4. 3 minus 0 is 3. Similarly, you carry on with all the other processes. You subtract maximum minus allocation to get the need. The available resources is 332 of type A, B, C respectively. Now let's check whether the system is in safe state or not. Whether I can satisfy the need of process P0 with this available resources. No, right? Since A is only 3, but it needs 7. This available cannot satisfy the need of P0. Let's check whether this available can satisfy the need of P1. So see here, P1 needs 1 resource of instance A, 2 resources of instance B, and 2 resources of instance C. But my availability of resource of instance A, B, C is greater than the need of P1, right? So I can satisfy P1 first. Let's say I give 1 instance of resource A and 2 instance of resource B and 2 instance of resource C. So my need will become 0, 0, 0, right? So my allocation will be 3, 2, 2, right? So all these maximum resources and allocation matches. So I can complete process P1 first, and then I release all these resources again back. So I will add these 3 to process A, then these 2 to process B, then these 2 to process C. So now my new availability will be 532 after P1 completes its task. Let us check whether P0 can satisfy. No, right? Because P0's A as 7, but my available A is only 5. So P0 cannot satisfy. Let's check for P2. P2's A is 6, but my available is 5. So P2 also can't be satisfied. Let's check for P3. So P3 can satisfy, right? Yes, because the P3's need is less than the available. Complete it now. So 5 minus 0 will be 5. 3 minus 1 is 2. And then 2 minus 1 will be 1. So my available will become like this. And my need will be 0, 0, 0. and my allocation will be 2, 2, 2. Now my allocation and maximum matches. Then I can continue with P3 to complete its task, and then finally it will release the resources which is allocated to it, that is 2, 2, 2, right? So it becomes 7, 4, 3. Now P1 is completed, P3 is completed. My new availability is 743. Now P0 can complete it, right? Since 743 is my availability and my need is also 743. Yes. So P0 can complete it and will release all the resources which is allocated to it, right? So at the end, it will become 753. It will become 753 from 743. The remaining process is P2 and P4, right? Can P2 complete its task? Yes, right? So P2 now can complete its task. Since the need is 600, my availability is greater than the need, so I can complete the task and then I'll release the allocated resources. So my current availability will be 10, 5, 5. Now P2 also gets completed. Can P4 get completed now? Yes, my available is 10, 5, 5 and my need is 10, 4, 3. So my P4 can get completed now, right? And then finally my available will become 10, 5, 7. This is one of the safe sequence. The system is in safe state. If there is at least one safe sequence, then the system is in safe state and there is no deadlock. So for this example, there is no deadlock. Can you think of one more safe sequence like this such that there will be no deadlock? So just work upon it and give your sequence in the comment section. In the next video, we will see about the deadlock detection and recovery mechanisms. How can we detect a deadlock and then how we can recover from a deadlock if such a situation occurs? We will see in the next video.